Hey everyone, and welcome back to the channel. Today we are diving deep into the microscopic world to explore the fundamental building blocks of everything around us. Atoms. Have you ever wondered what makes a diamond so hard, or why water behaves the way it does? The answers lie within the elegant and powerful structure of the atom. So grab your thinking caps because we're about to embark on an incredible journey into the heart of matter. Let's start from the outside and work our way in. Imagine a miniature solar system. Zipping around the center are tiny, negatively charged particles called electrons. These aren't just randomly flying about. They occupy specific energy levels or shells, a bit like planets in their orbits. The arrangement of these electrons is what defines an atom's personality. It dictates how it interacts with other atoms, essentially governing all of chemistry. Think of it this way: the number and placement of electrons determine whether an atom is a social butterfly, eager to connect with others, or a lone wolf, content to stay by itself. Now let's zoom in on the outermost electrons. These are the real VIPs of the atomic world, and they have a special name: valence electrons. These are the electrons in the outermost shell, the frontier of the atom. Why are they so important? Because they are the ones that do all the talking and handshaking with other atoms. When two atoms approach each other, it's their valence electrons that interact, forming connections called chemical bonds. These bonds are what hold molecules together. So whether it's the oxygen you're breathing, which is two oxygen atoms bonded together, or the salt on your fries, a bond between sodium and chlorine, you have valence electrons to thank. They are the master architects of the chemical world, responsible for creating the vast diversity of substances we see every day. So, if electrons are the planets, what's the sun? At the very center of this atomic solar system lies the nucleus. This is the dense, massive core of the atom. While the electrons are buzzing around, creating a large, mostly empty cloud of negative charge, the nucleus sits right in the middle, small but incredibly mighty. It's composed of two types of particles: protons, which have a positive charge, and neutrons, which have no charge at all. They're neutral. The number of protons is what truly defines an element. An atom with one proton is always hydrogen. An atom with 6 protons is always carbon. It's like an atomic ID number. The neutrons are important too. They add mass and help stabilize the nucleus, but it's the protons that give an atom its fundamental identity. Now let's talk about size and weight. This is where things get really mind-boggling. The electron cloud makes up almost the entire volume of an atom. If you were to scale an atom up to the size of a sports stadium, the nucleus would be no bigger than a marble sitting on the center spot. It's incredibly tiny in comparison to the space the electrons occupy. But here is the twist: that tiny marble in the center contains almost all the atom's mass. In fact, the nucleus accounts for more than 99.9% of the total mass of an atom. Protons and neutrons are heavyweights compared to the feather-light electrons. So an atom is this bizarre, fascinating object, a vast expanse of nearly empty space, with virtually all its substance concentrated in a minuscule point at its core. It's a beautiful paradox of emptiness and density. This brings up a critical question. The nucleus is packed with positively charged protons, and as we know from basic physics, like charges repel each other. So, with all those protons crammed into such a tiny space, why doesn't the nucleus just fly apart in a burst of repulsion? The electrostatic force pushing them apart should be enormous. Well, this is where one of the fundamental forces of nature comes into play: the strong nuclear force. As its name suggests, this force is incredibly powerful, but it only works over extremely short distances, the kind of distances you find inside a nucleus. The strong nuclear force acts like a superglue, binding the protons and neutrons together, easily overpowering the repulsive electrical force between the protons. It's the silent, unseen giant that holds the very heart of matter together. Without the strong nuclear force, nuclei wouldn't be stable, atoms couldn't exist, and the universe, as we know it, would be impossible. So, to recap, we have this incredible atomic structure. On the outside, we have the energetic electrons, with the valence electrons dictating all of chemistry and forming the bonds that create molecules. And at the center, we have the nucleus, a tiny, dense core holding over 99.9% of the mass, where protons and neutrons are, bound together by the immense power of the strong nuclear force. This elegant interplay between the electrons and the nucleus, between the chemical properties and the nuclear stability, is what gives rise to the elements and all the matter in the universe, from the simplest hydrogen atom to the most complex organic molecules. This fundamental blueprint is at the heart of it all. It's a testament to the beautiful and intricate laws that govern our reality, all playing out on a scale too small for us to see, yet responsible for everything we are. I hope this journey into the atom has given you a new appreciation for the hidden world that underpins our existence. It's a universe of forces, particles, and incredible design, all packed into a space smaller than we can truly imagine. Thanks so much for watching today. If you found this interesting and want to explore more of the amazing science that shapes our world, be sure to hit that like button and subscribe to the channel so you don't miss our next adventure. Let me know in the comments what other science topics you'd like to see us break down. Until next time, stay curious.